Recording in progress.
Hey everyone, how are you? Okay, right, so just as a reminder, there is an exam on Friday, so there will be the standard thing. I see that people have already been trying to look at the old problems, which is good, and yeah, we're going to have some questions. In theory, it would cover up until what we're doing today, but actually because today we're not going to finish talking about a whole topic, it's actually, the exam's only going to cover up until Monday. Today we're going to start doing something and we'll continue proving everything about it on next week, Monday. And then the way that the final exam works is the final exam covers everything in the course, and so all of the material today, Monday, and the next week are all going to be stuff that's included on the final exam. Okay, before we continue, I do want to mention for the exam, the standard procedure is that if anyone wants to take the exam at the alternative time, which is in the evening on Friday, the same time as it always has been in the evening on Friday, which I think is on the course website. If you want to do that, please send me an email before 2:10 p.m. Before 2 o'clock p.m. on Friday, on the exam day, and then that way you can take the one on the alternate time. I will make an effort to make the two exams somehow comparable in difficulty, but as you can see from all of the exams we've done before, the question types will be, of course, different in order to make it fair. Fair in the sense that people shouldn't get an advantage by looking at the earlier exam. Okay, are there any questions, by the way, about the exam that's coming up? It'll have all of the same rules as we've had for all of the previous ones. Okay, well in that case, let's continue on and let's discuss some more topics in graph theory. And just a second, let me make sure I'm on the right screen. Here we go. Let's continue to discuss more topics in graph theory. And although I say it won't be on the exam, it doesn't mean that this is not useful in the sense that thinking about graph theory in any sense is always useful for the concept of the exam. So the first thing I want to talk about is actually something that was on one of the previous exam questions, where I had happened to draw the notion of some kind of a graph, where the graph, you may recognize from a previous exam, had something like a bunch of vertices on each side, and all of the edges that were in the graph. I'm just like randomly drawing some edges here. Obviously I missed on that one, but like if I have some edges which are going on, I have some graph where I just randomly drew some edges which are always going between the two sides, between this left side and this right side. And this type of a graph, where you have somehow two sides and all of the edges go between the two sides, this is called a bipartite graph. And bipartite graph just means that there's a way to split the vertices into two sets. What's going on here is that there exists a partition of the vertices into two sets so that there are no edges within each set. Now, in this particular picture that I drew here, there are many different ways that you could make these bipartitions. For example, is there an alternate bipartition? Yes, there is. So if you look at a graph, there could be multiple different bipartitions that have this property so that all of the edges cross between. Can anyone see a way to amend this bipartition, make a change, so that I have, two different sets? Sorry, a different pair of sets, and so that all of the edges go between, or rather, there's no edge within each one. Does anyone see a way to amend this? Braden.
In the left set, left set,
Okay, let's give these some names. I called this V, I called this W. And another way to make a bipartition would be if we decided that the left set was like, was that we just switched V and W. That's what you mean. Like V and W are currently in different parts of the bipartition. Let's just decide to have, like, switch the bipartition so that V and W's presence or not is flipped. So what we can do is another bipartition with no edges inside a side is obtained by switching which sides V and W are in. And let me just draw that. And in this case, it's actually quite nice. If I want to draw it, I can really see it. I just want to make a bipartition where it contains W instead of V. And it just happens to be that I can do this by circling some stuff. Okay, I don't know if that's visible, but I tried to circle this piece to say that part is one part of the bipartition, and then the rest is the other part. What's the rest? I guess the rest looks like this. Hopefully this is somewhat understandable. I just tried to say my bipartition is going to be take all of the vertices on the left except that one, the V, and instead grab the one on the W. And if I look at what I've got here, actually there are no edges which are entirely within that clump up there. No edges entirely within this clump over here, and actually all the edges cross between. So I just wanted to emphasize that if somebody gives you a bipartite graph, it does not necessarily mean that there's only one way to make this bipartition. In today's discussions, we're actually going to be talking about bipartite graphs where we have certain meanings of the two sets in the bipartition. And that's okay too. But in general, if you have a bipartite graph, all it means is that there's some way to do this. And actually, technically speaking, if you want to ask, what if I want to say, could like the empty set be allowed? Yes, actually, it is allowed. So inside this bipartition into these edges in a set, the empty set's allowed. If you manage to find one that way, that works too. So empty set is okay. But actually, if you think about it, what kind of a graph would that be? If you had a bipartite graph, let's just ask this general question. And I'm doing this because, you know, for the exam, we're going to have all kinds of questions about graph theory, even though I said we won't use the main theorem that I'm about to state and prove today and next time. This general discussion is useful. Can anyone think of what does the graph look like if someone told you, I have a bipartite graph, and it happens to be bipartite with a partition where one of the sets is empty? You can actually say what the graph is at that point. Andrew.
It's just a bunch of disconnected vertices.
Yes, that is true. Here's like random note. This is just like practice. But like if you have a bipartite graph where the bipartition is empty set union everything, every vertex, then the graph is just vertices with no edges. I mean, that's just like what the definition would say, because I have these two sets, which is called nothing and the everything. This is the nothing, this is the everything. And the rule was that you have no edges inside each piece. But of course there's no edges inside the empty set, because there's no vertices anyway. And so the whole graph is just a bunch of vertices. Okay. Now, one of these standard things is like, well, if I want to know if a graph is bipartite, how easy or hard is that? You know, if somebody just gave you a graph and said, I wonder if it's bipartite. Well, in theory, you have to check all of the different ways of splitting it, right? So here's a general question. How to check if a graph is bipartite? At first, it looks like I've got to try all of the different possibilities of bipartitioning and see whether or not they're okay. Okay would mean there's no edges inside each set. So here is one answer, and not question mark, it is an answer. You could do it by trying all of the bipartitions and seeing if any of them are good. And good means that it happens to be that somehow all of the, like if I look inside a piece, there's no edges. Inside each set, no edges. Okay, how long would that take? Roughly speaking, how many ways are there? How many ways are there if I have n vertices to go and find all of the bipartitions? Like how many bipartitions are there of n vertices? Does anyone know? I'm saying if I have n vertices, how many ways can I split that into two different sets? Ah, Sean. Yes, what do you have to say there? That's good.
Yeah, it's just like each vertex goes in one of the partitions. You choose two things n times.
Yeah, there are 2 to the n ways to decide. For every vertex, is it in the left side or the right side? Is that okay? I guess left and right are kind of weird, but like part 1 or part 2, let's call that. To decide for each vertex, if it's in part number 1 or part number 2. Now, technically speaking, I could save a little bit of effort, because if I'm talking about bipartitions, I have a little bit of symmetry here, right? It's like if I said this is part 1 and that's part 2, and I said, well, I did another one where I said this is part 1 and this is part 2, those are somehow the same bipartition. And so I could save a factor of 2, maybe. Great! So 2 to the n minus 1. Am I happy? No, I'm terrible. This is too big, too big. 2 to the n takes far too long. Like, this would not be a practical algorithm. So I'm going to say, in theory, you could save a factor of 2 by symmetry via part 1 and part 2 names. Okay? But that's still exponential. In the number of vertices. Oh, I should probably have emphasized what is n. N is the number of vertices. Almost every graph theory thing, n is the number of vertices. So, n is the number of vertices. Okay. No odd numbered loops. Okay, now this is interesting. So we're trying to find like more efficient ways to do this. Jutya, what are you saying? Tell me more.
Well, if there is an odd numbered loop and you just pick one to start and put one on one side and then keep playing it by the end, where you're gonna have to connect two things on the same side.
Okay, so let's give this a name. Let's call it an odd cycle. If there's an odd cycle anywhere. Odd cycle anywhere means like a cycle with an odd number of vertices. Okay. If there's an odd cycle anywhere, well then there's no way you can do this. Like if there's an odd cycle anywhere, then somehow you're gonna be stuck. There's no way to decide which sides things go on, because all right, you'll be stuck. You'll get stuck on how to sort of like split the vertices into the two sides. Into the two sides. Okay, so why? Because like suppose I have an odd cycle. So let's draw typical odd cycle. Oh no, I want to have 5. 5 is a nice odd number. Actually, 7's a nice odd number. Let's do 7. 1, 2, 3, 4, 5, 6, 7. There, 7. So I just drew 7. So now the issue with this odd cycle is that if you're trying to decide how you're going to split the vertices, well, maybe this guy goes in side 1. I don't know where it goes. It goes somewhere. But then if you try to put the next vertex in a side which is different. Like the key is that, I guess that's the key. The key is if I have a vertex in one of the sides, well then every vertex that's adjacent to it must be in the other side, because that's the rule. Bipartition means that I can't have one side which has two vertices which are both endpoints of the same edge. So the important thing here is that every edge means you must flip the side, let's not use the word flip, must have both endpoints in opposite sides. Both ends in opposite sides. Actually, I'm now realizing that, no, so we are actually going to do like two things. So when I said that there will be nothing today on the exam, that's actually not true. We could potentially have some part of today on the exam. Basically, at some point, I'm going to start talking about matchings and Hall's theorem and something. There will be something I don't finish proving, and that part I'll make it clear. That part won't be on the exam, but we're actually going to legitimately finish a certain section of very nice stuff that could be on the exam, but also will probably make a lot of sense for you anyway. So it'll make you happy if this sort of thing can be on the exam. But anyway, so like as we go on to this, and I mean that in a good sense. It's like we're going to talk about something. It's not going to be theoretically extremely crazy, and I'll be like, yeah, that's also fair game for the exam, right? But now the deal is like if I have an edge here, right? If this thing is in one of the sides, like let's call it 1, now I'm forced. I have no choice. This one has to be in the second part. I'm trying to say, could I split these into two different parts with no edge inside a particular part? Okay, so that forces the 2. And then that forces that this is a 1. These are all forced. And then this is a 2, and this is a 1, and this is a 2. And oh no, now I suddenly forced my way around the odd cycle, and I got 2 of these endpoints, and I got forced that it has the same part as the other one. That's just why odd is important, right? So the issue is that as you go forcing all around, but forcing all around, let's write this more legibly, forcing all around implies you get 2 same sides on ends of the last edge. And that's where we used the odd cycle. Okay. So what you have just shown, thank you, Trisya, what you just showed is that if there is an odd cycle, then it's not bipartite. Then it's impossible to go and split the vertices into these 2 sides. That's very satisfying. That's not exactly what we're done yet, what we wanted to do though. What we wanted to do is to get a criterion or a way of, we want to prove something. We're not done proving, I guess, is what I mean to say. We want to prove something that says, hey, here's a way to know whether a graph is bipartite. Exactly this condition. When this is satisfied, it's bipartite. And when the condition fails, it's not bipartite. You have just proved something about when a certain condition fails, then it's not bipartite. And the condition is called no odd cycles. You are going in the right direction. But I just want to write down what you have just done. What you just showed is if there is an odd cycle, not bipartite. So now we know if there exists an odd cycle, then it's not bipartite. And that's kind of a very nice statement. It's like, well, if there's not an obvious, well, here's an obvious blocker, odd cycle, it's bad thing, then it's not bipartite. But it turns out that there's also a nice theorem that goes in the other direction, which shows that what your condition is good, which is, theorem says, if there are no odd cycles, then it is bipartite. So then that's very satisfying, because if I can show this theorem, then we know that bipartiteness is equivalent to no odd cycles. And that's actually how a lot of us think about this. Like, if I want to know whether a graph is bipartite, hunt for odd cycles. If I don't see any odd cycles, it's good. So let's now prove the theorem. And that's why I said it's like both sides, right? It's like if you have one of these odd cycles, no, you're dead. But otherwise, you're good. It's bipartite. So how do you prove this theorem? The reason this is a slightly different thing to prove is because I can't just be like, well, I I can't not succeed or something. You know what I mean? Like if I want to show that it is bipartite, I'd like to show a way that I could say every vertex, here's what side you're on. Can anyone help me out with that? If I just guarantee for you that the graph has no odd cycles at all, can you show me a way that I can now attempt to split the vertices into two different sides and by the end say, yep, I have no edges inside each side? Braden.
You can start by just choosing some vertex on your graph and putting it into, say, the first group. And then after that, you always switch groups whenever you move along.
Okay, so let's see. So you pick any vertex, you put it into part number 1. That's the easy start, right? Let's just start it in part number 1. Doesn't make a difference anyway. Now there's some edges that it's connected to. Okay, it's got some edges. And what you're saying is, well, I have no choice, right? I'm supposed to make a bipartite. So let's just try. Let's just try to put it into part number 2, if it happens to be coming out. So what you do is you're going to say, put those in 2's. Put all its neighbors in part number 2. Well, you could be in bad shape, right? Like, what if there was one of these? Then you'd be dead. Like if there was a connection between them, then that's bad, right? We're trying to show that we managed to split into 2 parts and you never have an edge between 2 things with the same label. That would be bad. So I need to show why not. Why this doesn't happen. Can anyone tell me why that doesn't happen? Why don't I end up getting 2 vertices which are kind of like both assigned to the 2 and they're adjacent? Well, yes, Andrew.
Because that would be an odd cycle.
Yes, since that's a 3 cycle. That's a 3 cycle, and 3 is odd. Okay, but that's how this is all going to work. Because now the deal is like, now I know that's not going to happen. Okay, that's good. I'm going to go to the next screen and just start to draw something. And I'll even show you a convenient way to draw this. So we start with this vertex, we called it a 1, and we have some neighbors. But the next screen, I'm going to diagram them in a different way. Like here's this 1, and here are its neighbors. Okay. All of these neighbors got called 2. And then all of those neighbors have neighbors. By the way, you can actually have stuff like this. It's entirely conceivable that you have those neighbors have a common neighbor, or it could just kind of go off, or you could have like multiple things as it spreads out, or you could have like one of these guys which doesn't just doesn't go any further. Okay, these are all possible. What should we label these guys? Where should we throw them? We should throw them into 1, right? We should throw them into side 1. So we'll call them all 1s. And then we just keep going. So now, as we keep going, sometimes these things expand massively. Sometimes they don't. Sometimes they cross-connect in weird ways. Okay, and the next ones are 2. I'm drawing this on purpose. It looks kind of satisfying. Everything is going across to the right. And if you can see, I somehow didn't have any teleporting edges. Like I didn't have any edges, like somehow I have these layers, right? If you look at what I've drawn, I have all of these layers. This is this first vertex. Here's the first layer, here's the second layer, here's the third layer, and so on. I can even give these layers some names. Like somehow this is the vertex V. The first one I'm going to call N1 of V. N stands for neighborhood. The next one I'll call N2 of V, and the next one is N3 of V. This is like how you analyze a graph often if you're playing with graph theory. All of the N stand for neighborhoods, so I would often call this the first neighborhood. The N2 is the second neighborhood, the N3 is the third neighborhood, and so on. And if you can see, the way that this is all laid out is that we just start from this first vertex and we go and see who can we get to. And then from anywhere we can get to, we go and see where can those guys get to, and where can those guys get to, and so on. Now, if you look at the way I've drawn this, it's really nice because I have no edges that go between neighborhoods which are far apart. Somehow all of my edges go between like the second neighborhood and the third neighborhood. But I have no edges between the first neighborhood and the third neighborhood. Why? That's a nice fact. No edges except between like neighborhood K of V and neighborhood K plus 1 of V. If you look at what I've done, like the only kinds of edges I ever have. Oh yeah, and you might wonder, what about the V? You could call that N0 of V if you wanted to, and I guess that would be good too. But why is it that I don't have any edges that go like teleporting between faraway things? Jack.
I just noticed that if there's an edge that connects at the teleports, then it's one of the neighbors, right?
Yes, that's good. So it's like if you had one of these teleport things, then it's like, hang on a second, why did you put that vertex all the way out here in the N3? If it's already adjacent to the N1, then you should actually have it already in this N2 layer. Okay, so this is just saying the way we're constructing these layers is we're constructing the layers where we're saying, here are all the vertices which I can get to and how fast can I get to them. In fact, they also correspond to distances. They correspond to graph theoretic distances. In fact, everything at N1, these are all the things which are graph theoretic distance exactly 1 away from the vertex V. N2 are all the things which are graph theoretic distance exactly 2 from the vertex V. The graph theoretic distance is saying what's the shortest number of steps that I need to take to get there. And so the observation actually has two parts. When I say the only edges are between successive ones, the first part is no teleport, no jumps. Since otherwise, the later, well, I'll write it this way. The n bigger V vertex should have been in an earlier n something of V. Okay? And I made this comment about that these are like graph theoretic distances too, which is quite nice. So here's just like nice observation. These are also all vertices at graph distance 2 from V. And the graph distance is like the shortest number of hops you can take. Okay. And so that's I wrote this 1 here. There's no jumps. So I can't go from like an N1 to an N3. But why did I write a 1? I wrote a 1 because there's obviously going to be a 2. So if I'm making a statement that says the only edges go between nk and nk plus 1, why do I have 2 things to prove? One of the things to prove is I can't fly too far. What's the other thing I need to prove? Subhashish. Yes, the other piece is that there's no edges in a single nk V, since, well, why not? Suppose there was some edge inside here. What does that mean? So suppose I have any edge inside this N2. I need to contradict something that I used as an assumption to begin with. Got some people. Oh yes, Isain. Okay, so that's going to give me an odd cycle because you see, I'll get this edge here, and from both of those endpoints, I can walk my way over to V. All right? I will give one little nuance there. The one little nuance there to be careful of is suppose I've got a v, and suppose all the way out here I have an nk of v, and suppose I actually got an edge somehow. Now, even though I have an edge there, if I think about how it gets its way back to v, it's like it goes back to v by walking along consecutive things. And in the easy case, I get something like this. And that's an odd cycle. The reason that's an odd cycle is because it's like k plus 1. Good. There's another possibility, though. You could also have the vertex v, but the other possibility is also good. Nk of v, and here's my edge. Actually, can someone tell me what I mean by the other possibility? There's another thing I wanted to say. Like, this is like clearly an odd cycle. And I'm saying I'm walking my way back. I'm walking my way back. On the other one, just, yeah, yes.
Could meet before v.
Yeah. So they could actually meet before v and then continue on. But that's also an odd cycle. Is that clear? It's like I'll meet. So I won't be like k plus 1. It'll be something else plus the same thing plus 1. So we're good. So what we have here is that this is telling me that I can't have anything except just these edges which are going across. Oh, well, that's really satisfying. In that case, that's a bipartition. The reason that's a bipartition is because the only edges that I ever get are between things labeled 1 and labeled 2. So this gives you the bipartition you want, with like one little annoying piece. It's like, hang on a second, this works if the graph is connected. What if the graph is not connected? Now what? You know, like if the graph is not connected and I just kind of go, at some point I run out. There's like no more stuff to expand to. Then what do I do? If the graph was disconnected, I need to still be able to label every vertex with a 1 or a 2. So, Jitya, yes.
Could you just do the same thing on separate blobs?
Yes, that's it. So the thing is, if the graph is disconnected, just do this separately on the separate blobs, and it works. So that's it. So, and I'll write the last thing here, is like if the graph is disconnected, just do this on each connected component. Okay. And I wanted to share this particular kind of a decomposition because it's really useful. And it sort of lays out all of the edges in a nice way. And you can actually do this for every graph. It's just that for other graphs which are not bipartite, item number 2 won't be true. Item number 1 is always true. So the important thing I want to say is this particular kind of a decomposition, you can use this decomposition on any graph, and you'll at least get the first part, which says that the edges go like between successive parts. But if you do this with an average other graph, which is not bipartite, you could potentially have some edges over here too. Okay, but that's just like an interesting way of taking apart your graph. All right, so now we actually have proven, by the way, that if I have no odd cycles, then there is a way to go and label everything. This is great. And so we now have a rule. If I want to know whether a graph is bipartite, I no longer need to go and check all the possible partitions. Instead, all I have to do is look for all the odd cycles. How many odd cycles are there to check? Wait a second. This looks worse. So if I think about it, like, how do I check all the cycles? Well, in theory, if I had like a very connected-ish graph, you know, if I want to know how many cycles there are, I almost have to be like, well, there's n ways to choose the place to start. And if it was really, really interconnected, maybe there's n minus 1 ways to choose where I go next. Oh no, maybe there's n minus 2 ways to choose where I go next. It's looking factorial-ish, which is even worse. So at first, it looks like if you say, don't worry about bipartitions, worry about looking at cycles, you, in theory, could be looking at a ton of possible cycles. Chris?
You also know that if the edges are past a certain threshold, then it can't be bipartite at all, so that puts it down.
Ooh, I want to talk about that. That's good. So that's actually an interesting question I want to hit. So here's an interesting point. You were like, wait, but look, come on. If it's so dense, it's just going to be busted, right? If there's too many edges, of course there's going to be an odd cycle, right? So you have this notion of like too many edges gives me an odd cycle. So perhaps hunting over all cycles won't be that bad. Well, then that suddenly asks a deep question. How many edges can I get with no odd cycle? Do you know what I mean? It's like, how bad could this be, right? Like if you just imagine you're starting to draw this graph and you're adding edges and you're throwing them down, it's like, come on, eventually I'm going to make an odd cycle. This is asking a general question. This is a question in extremal combinatorics, which is, what's the max number of edges in a graph with no odd cycles anyway? That's a nice question. Can anyone think of a graph that has a lot of edges, which has no odd cycles? Andrew.
You could like take the neighborhood thing we just drew and maximally connect it between each
Okay.
and k.
So you're like, let's just do a bunch of this stuff and like this. Is that what you mean?
Yeah, exactly that.
Okay. That's good. That's a good start. I mean, that's a really good step. But how many blobs should I have and how big should they be? I want like the most possible edges. This is in terms of n. In terms of number of vertices, which is n. Chris.
If you go back to the original bipartite graph, so you're going to have, so in the worst case is when they're even, and n over 2 on the left side and
Okay.
n over 2 on the right.
Yeah.
And then for each vertex, if it's connected to every other one, then that's n over 2 times n over 2.
Okay, so it turns out that this actually has more edges than this one. And the reason is because if you think about it, in this one here, which we drew, if you had like, this is in category 1, category 2, category 1, category 2, category 1, and the other one has category 1, category 2. If you think about the first one that we drew, we are connecting some of the things in 1 with some of the things in 2. Does that make sense how I've said it? Because like, you don't always connect everything in the 1 with everything in the 2 because we skip some of them. Like here's a 1 and here's a 2, right? And in the second drawing, we just said, look, if I want the most number of edges, my only rule was no edges inside a category. So let's just put everything else that we can. So this is going to be more. And there's like something, maybe you've seen these kinds of problems. It's like, if I have two numbers which add up to something and I want the biggest possible product, because that's the number of edges, you make them balanced, you make them equal. It's like this classic problem, right? It's like they tell you, I have, 10 miles of fence. What shape should I make in order to enclose my ponies in a fence? Like what's the optimal shape? And the answer is, of course, a circle. But no. So I mean, if you wanted a rectangular piece, then it has to be. All these questions are like, for whatever reason, you decided that you want to make rectangular fences, and then the answer is make it like equal as a circle. Oh, Aaron, you have a question or something? Oh, cool. Okay, thank you. Right. So the deal is like, actually, this is how many you can make. And over here, the number of edges, by the way, is n squared over 4. You might say, what if n is odd? Well, then round something. That's not what we'll focus on here. But over here, the number of edges is like n squared over 4. So unfortunately, that's actually a lot. so unfortunately, that's a lot. Because if I have this many and I'm trying to say how many odd, like look over all the odd cycles, if you're trying to build an odd cycle, you might be like, let's just try to go around. Here I have this vertex. I have n choices for where I start. I have n over 2 choices of where I can go to. Like, you know what I mean? Like you could, in theory, have n factorial-ish type things, which is too many. So this is interesting, by the way. This is actually the maximum, and you can even prove that, but we won't do that today. So then, great. It turns out that looking over all cycles is kind of painful. So actually, it turns out that the thing we just did with this decomposition, this is a very efficient way to figure out if a graph is bipartite. Just do this. When I say just do this, what I mean is, for each connected component, grab a vertex and attempt to start painting it by actually making this exact decomposition. That's why I showed you the decomposition. If it happens to be bipartite, you will succeed. What I'm saying is that if you follow this procedure, if it so happened that there were no odd cycles, then you just like go all the way through and you'd be done, because we already did that here. What if there is an odd cycle? Well, then you'd find it. Do you know what I mean by you'll find it? That's why I emphasize that this particular thing you do with the neighborhoods, the neighborhood decomposition always gives you the yellow thing, number 1. It's just that sometimes it gives you the number 2 and sometimes it doesn't. When it doesn't give you the number 2, you get stuff that looks like this. Like, the important thing about this decomposition is number 1 says there's no like flying or teleporting, but you might have edges inside the same piece. But what we just saw right here is the moment you see one of those edges, it's like, bang, look at that. That's my odd cycle right there. Did that make sense? Like, this is actually a very efficient algorithm for going and figuring out if a graph is bipartite. Just go and grab vertex, start doing this fanning out process, and there's not like a lot of backtracking you have to do. The reason why going over all cycles is hard is because you have to be like, well, I did that cycle. Oh, but how about that other cycle? And like that other cycle where I changed my mind and I keep trying all these different cycles that overlap. With this one, you just lay out the fan and you look, is there ever an edge inside the same piece, inside the same like level? And if there is, odd cycle. If there isn't, oh, I'm looking at a bipartition right there. Did that make sense to people? So this just turned the problem of like look over an exponential space into looking over a factorial space into looking over a polynomial space of just laying all of this thing out. Okay, so now we have found out how to figure out whether a graph has bipartitions. That's nice. It's easy. You just lay this out. So, you know, like what we always do in math is we're like, well, if we can do that, let's just do the next thing. What do you think is the next thing, the next easiest thing? About the first thing was, is it possible to check whether a graph is bipartite? What would be the next question? Tripartite, why not? You know, like it's just like if we did the bipartite, let's do the tripartite. How hard could that be? So what's a tripartite graph? Well, let's do a definition. Definition. We can say a graph is tripartite if you can partition the vertices into 3 sets. Remember, sets can be empty, possibly empty. So that each set has no edges inside. By the way, every bipartite graph is automatically tripartite. Is that clear? Like if I had a bipartite graph, how do I make it tripartite? I just go and say empty set is my friend, and now I have my tripartition. So here's like very easy fact, observation. Bipartite implies tripartite. So then here's this really simple question. How to tell if a graph is tripartite? Well, I guess one way is just like look over all the possible tripartitions. That could be done, that'll be exponentially big. Is there anything else we can do? Well, actually, if you figure out the answer to that question, you get an automatic A in this class. Okay, so like this is a very, very, very hard question. In fact, also after you solve it, then you might disappear because the National Security Agency might declare that you seem to know something that they want to know. This is why I personally never work on such problems, because I don't want to disappear after solving them. But some people like to solve these. Good for them. Oh, you know what? Maybe that's why we've never figured out that we never heard of anyone solving it, because anyone who did disappeared. But that's a deep meta question. But the bottom line is like this is actually extraordinarily difficult. And the reason why it's difficult, well, the reason why it's not easy. I can't say the reason why it's difficult. If I knew why it was difficult, I would have a proof of p is not equal to np, and then that would be pretty good. But nobody actually knows why it's difficult. We just think it's difficult. But the reason why that easy thing doesn't work anymore is because there was a very interesting notion of forcing, okay? So I just wanted to just point this out, because some people, including me, the first time I saw this, I was like, what's the big deal? Bipartite, tripartite, what in the world changed? 2 and 3 are basically the same. They're like both numbers, right? But here's why the odd cycle thing doesn't help. Well, remember if you had bipartite testing, that's what I'll call it, bipartite testing. We were looking at this odd cycle here. I just draw 5 things. And there was this interesting notion of forcing. Ooh, what's this? Why can't you do non-3 cycles? Okay, actually, first of all, Chris, what do you mean? That sounds interesting. What do you mean?
Like, no, you can't, or,
Oh, I understand what you mean. If
yeah.
there's this thing, then it's not tripartite. Is that what you mean? You are correct.
Yeah.
Okay, that's a very good statement. Like, if you see this thing, no way in the world can you go and put the vertices into 3 parts. Wait, no, that is tripartite. Sorry, next one up, next one up. No K4. Let's put that one in. If I put that there, nope, it won't be tripartite. Why it won't be tripartite is because if I attempt to like tripartition even that little piece, those 4 need to be in different parts. Is that clear? Like these 4 are all insisting they're different parts. Actually, whenever you're thinking of partitioning graphs, you can almost think of it as like this is like the anti-Facebook. These are not friends. You cannot put them in the same place. They repel each other. That's what this is. So if you have this thing, these 4 people repel each other. They have to be in 4 different pieces. Okay? And so that is true. But the problem is that the opposite is not true, in the sense that there are graphs which just so happen to have none of these pictures, but are still not tripartite. What I mean is that if we wanted to have this beautiful condition, I would need to have a statement that says, well, if the condition's here, then it's tripartite, and if it's not here, it's not tripartite. So I'll just write down, unfortunately. But there are graphs with no this and still not tripartite. Actually, I'll give you one of them. This is a very famous graph. This graph looks like a pentagon, but it has another star inside, and it's got like this. This is a graph which has no K4. That's what you drew here. And it actually turns out that you can't 3-color this. Is there an easy way to see that? I'm not sure I can prove that immediately for you guys here. I'm just going to try. Like, suppose I tried to color it. That one's a 1. This has to be different. That has to be a 2. Oh, no. Now it's going to be painful. So I actually will say I can't easily give that to you. But this is one of these things where you can check that this is actually not 3-colorable. And this is called the Peterson graph. I forgot whether Peterson is P-E-T-E-R-S-E-N or O-N. So I'll just write that. So it's an ambiguous E and an O. But it's either a Peterson with an E or a Peterson with an O, something like that. But this is this Peterson graph, which is a classic counterexample in combinatorics. And so this is something which has it has no K4, but it's also not. Actually, wait. Now I'm thinking. I might be misremembering. This one might actually be tripartite. Let me pause. Let me not actually give that example because that might be wrong. But the Peterson graph is a useful counterexample for other things. But in any case, I'll say there are some graphs here which we won't dwell on today. So the important thing is that this is not like a exact characterization. And now one of the things is like, why over here in bipartite testing? Oh, and somebody found the actual spelling. Thank you, Abby. So over here, what's different about using 2 parts versus using 3 parts? Well, the situation is, if I had some color, I already said the word color, but if I decided to put it in some part, if I decided to put that vertex in some part, notice there was a notion of forcing because there's only 2 parts to play with, and I have to choose a part that is not the one I've already picked. So what's going on with this edge? Edge makes 2 minus 1 choices, at most 2 minus 1 choices, for the next vertex. Is that clear? I had 2 parts that I could put things in, so I have to avoid one of them. So I get 2 minus 1. 2 minus 1 just so happens to be 1. So there's no branching. That's the key. There's no branching. But if I had tripartite testing, well, I put a 1 there. I've got some choices now. This guy could be 2 or 3. So suddenly, the situation with tripartite testing, that was supposed to be a question mark, tripartite testing is that now suddenly over here, this is at most 3 minus 1 choices. But that's 2. And that's the same problem as something called COVID. What I mean is that this is like the exponential growth. There's a base of an exponent. And the base of the exponent is more than 1. The problem is if you have a base of an exponent which is 1, there's not much I have to check. It's just like forcing me all the way around. But over here, suddenly my base of the exponent is 2. And that's just like a very, like in a nutshell, why is there a difference between bipartite and tripartite? 2 and 3 are about the same. But once you subtract 1 from each, 1 and 2 are fundamentally different, because one of them blows up as a base of an exponent. So anyway, I just wanted to share that out with you. So this is this notion of bipartite graphs, tripartite graphs. How to find a graph is bipartite, you just like do that like neighborhood expansion thing. Same thing as no odd cycles. How to find if a graph is tripartite. Cool, nifty question. If you like it, and I encourage you to think about it. Actually, it's quite interesting. And also, I should be careful. I don't want to dissuade people from thinking about these things. I shouldn't have been so glib about saying you'll be disappeared by 3-letter organizations. That hopefully won't really be the case. And indeed, there are lots of people who are trying to figure these things out. With that, that finishes what we're doing. Actually, everything that we talked about today, hopefully conceptually, is pretty tight. And at that point, what I did is I'm putting this other stuff about Hall's matching theorem into the next week. And that way it's clean cut. Things that we talked about today, we could still put on the exam. But hopefully it's made enough sense that that's a good thing. Okay, I'll see you guys on Friday. Oh, question. If someone proved P equals NP in a non-constructive way, would it like change anything? Well, that's a good question. If you ask me, like, if somebody proved that P equals NP non-constructively, I think that would suddenly make a lot of governments spend vast resources to attempt to find a constructive proof of it. See, what I'm saying is the moment that you know that P is equal to NP, meaning that these complicated things can be done efficiently, even if you don't have a good way of explicitly making algorithms yet, the sheer fact that it's possible will attract tons of people and tons of money to find a way to like make it work.